Okay. Hello, everyone. Welcome to our Prague seminar. If for online participants, if you want to ask question, then maybe don't use the chat, but just turn on your mic and ask directly. That's as far as the technical issues go. Okay, so we are very happy to have this week Thomas Weber from Charles University.
Correct.
So please.
Thanks. Yeah, thank you for having me. This is actually kind of a part 2, because last year I spoke about some topic very similar to this one. So maybe this is a bit more.
Yeah. Have it worked before?
But maybe I can continue to talk.
Yes, try. Okay, now try this one. Good present. Okay, can you go? We will be back after again. And remove the annotations. I'm not sure if that helps. Maybe now.
I can feel that the spirit of Nadi is with us.
Guys, you see the page counter at the top of the slides.
Yeah.
To the right, there is a button.
Page counter. You mean this one?
Yeah, and I think the next one will allow you to.
Fit to it.
Yes.
And
then press it. Well.
Oh, nice.
No, I'm sorry. This is not it.
You should try to switch to a single page mode then.
Oh, sorry. It should be full screen now.
I think it was double page mode. Okay. Thank you. Wait, sorry. Now it's
F11, sir.
F11. See
And then press on the sandwich near the title.
this one.
No, near the title of the leftmost sandwich. Or
Sandwich. Yeah, this one. Okay, this is better, but not still ideal.
And you can try to feed it.
Yeah, but let's make it, this is manual thing, then we should go somehow like realistic. Yeah. I mean, it was working like moments ago when we started, and the next time we are using moments. This is ridiculous. Okay, share this tab. Just need to break it. Now maybe if we unbreak it. This. It's not that bad. Okay, maybe this way.
Click several times on this. Yes, once again. Now press F11.
This is the best so far.
That's the best.
Okay, perfect.
Okay, great. So after some technical issues, we are back on track. So, okay, thanks for having me. As I said, so last year I gave a seminar about the first paper that you can see here. And this is a joint work with the Green group. So it was with Adizoni, Bottigoni, and Chandra. We managed to publish this paper earlier this year. And of course, since last year, quite far, I think it's fair if I also recall stuff that we did there. So in this paper, we introduced what we call infinitesimal braidings. So you can think of them as like first order deformations of braidings. And in the second paper that you see here, it's a preprint on the archive. Currently, we are trying to quantize them. So kind of get an honest braiding out of an infinitesimal braiding. And yeah, that's kind of the task of this talk. So I will start the motivation with something very basic so that everybody is on board here. So let's have a look at G, a complex semi-simple Lie algebra, and let's take a look at the Casimir element. So this is this C that you can see here. So if you choose a basis of G and a dual basis, then you can use the killing form to identify your dual basis with an element of the Lie algebra. And then you simply sum over this dual basis elements. And this is what gives you the Casimir, something very well known, very well studied. In fact, we can do the following. We can apply this delta C, so the co-product to the Casimir, and try to see how much this is not a primitive element. I mean, we can see on the nose that it's not primitive because it's the product of two things. It's probably not primitive. And in fact, you can see the difference of the co-product of the Casimir with 1 tensor C and C tensor 1 gives you this expression on the right-hand side. That is an element in G tensor G. And we call this chi, right? What properties does this element have? So first of all, it's an invariant element, and it commutes with the image of the co-product. Okay, very well. Nice to have such an element. For example, like the easiest case, you can think of your lead algebra as SL2, then your chi would read like this here. So what we will do is kind of a naive thing. So we say, what happens if we take the exponential function of this chi? What do we get here? And kind of our dream would be that this is an R matrix. If you don't know what the R matrix is, later on in this talk, I'm not going to tell you. But for the moment, think of this as an element of the tensor product of the universal enveloping algebra that then will give rise to a braiding on the level of modules. So this will tell you how to move objects in your category. And yeah, our idea is to say maybe simply e to the power chi will give such an R matrix. It's a naive ansatz. And so here I should also mention I take some formal parameter here that I call the Planck constant. So in principle, there's some technical thing that you extend your universal enveloping algebra, everything in an H-bar linear fashion, so that you view this as a topological Hopf algebra. This is some technical details that we're not so interested in at the moment. So the question is this an R matrix? And of course the answer is no, because we do not have nice things. But it's kind of close. It's almost like that. Namely, what you get is a quasi Hopf algebra. So it's not really an R matrix, but quasi. Yeah? And I'm going to tell you what this means. So if you do not look at the blue stuff, then you would have a usual quasi-triangular Hopf algebra. Now, quasi means that you have an element phi that is kind of making your formulas more complicated. And yeah, this is what you get. So you don't get a quasi-triangular Hopf algebra, but a quasi-Hopf algebra. So let's talk a bit more about this phi that you get. This is an element of the triple tensor product. And this is what people call a reassociator. Those are objects you can find. So the most famous one is this phi kz that you get if you solve the Knizhnik-Zamanovnikov differential equation, something that I don't want to do, but some people did. So you can find such elements. And so why is this interesting? Why should we care? So this is kind of my motivation, is that you realize that this quasi-Hopf algebra that you get is almost the same thing as the very famous Dirichlet-Jimbo Hopf algebra. So you just need what some people call a gauge twist. So you gauge twist your quasi-Hopf algebra and you get an honest Hopf algebra, so no quasi. And the thing that you get is the Dirichlet-Jimbo quantum group. That's something that is very useful in mathematical physics and people like it. So kind of the idea would be Dirichlet-Jimbo interesting but complicated. Like there you have a rather complicated coproduct, a rather complicated R matrix. While on the left-hand side, you have a very easy coproduct. I mean, that's just the primitive coproduct that you extend in an H-bar linear fashion. And also your R matrix is very, very easy. It's just e to the H-bar chi, where chi is built out of this Casimir. The only thing that makes the left-hand side complicated is this phi. Yeah? So if you're fine with working in the quasi world, you might say the left-hand side is even easier than the right-hand side. Okay, that's kind of the motivating part. And so our question is, can we do something similar? Because Dirichlet-Jimbo is nice. Can we build similar Hopf algebras? So the first question would be, can we think of something like a Casimir in a context where there is no Lie algebra in the background? So what would be this chi? And this will then lead to the notion of an infinitesimal R matrix. So this is the thing we came up with in the first paper. So we're going to study this a little bit. This will replace the Casimir. In a second step, this will be in the second paper, it's the question would be, can we use a similar quantization ansatz? So it's simply putting e to the power chi to get some kind of R matrix, some kind of braiding. And the answer is, yeah, this also works. And this is part of the second paper. And the last step then would be, so what do we get after gauge twisting? Do we get some kind of infinite limbo algebras here on the right-hand side? And this is the part that we did not answer. This is still work in progress. Because it's probably the most interesting, but already the first and second step were not so easy. So yeah, step by step.
What do you call it, the reassociator?
We call it the re-associator because it's not a Drinfeld associator. Those are two different things. Like a Drinfeld associator is a machine that gives you several re-associators, while the re-associator is an element of a particular Hopf algebra that has similar properties. They are very closely linked, but it's not exactly the same thing.
Okay, so it's not like a formal element and formal, then it's concrete for the algebra.
So it is a Power series, as you see.
Right, but I mean, it uses a Lie algebra.
It uses a Lie algebra, definitely. Yeah. And it is even built, if you want, out of a Drinfeld associator that is in the background, and you plug something in, and you get this file. Okay, so this was the motivational part number one. Maybe this is now motivational part number two. Throughout this talk, I'm going to switch between category and algebra. There is this credo that category theory and algebra are kind of the same thing, which is of course not true, but what I mean by this is that if you start with an algebra H, field, let's say, you look at the category of left H modules, this is what we call here is HM, then for every extra property on the level of the algebra, you get something on the level of the category of modules and vice versa. So it's kind of, you can learn about H if you have more information about the category of modules and vice versa. So explicitly what we mean by that is, so this category of left modules is a monoidal category. So we have a tensor product. This happens precisely when your algebra is secretly a bi-algebra. So when you also have a co-product and a co-unit, we're going to see on the next slide, I think in 3 slides or something, how this actually works. If you have even more, if you have a braided monoidal category, then on the side of algebra, you get what's called a quasi-triangular bi-algebra, where now your braiding will correspond to a universal R matrix. That's the thing that's also mentioned in the first slides. And what we came up with in the first paper was, okay, so now we want even more. So we have a braided monoidal category, but some extra structure, some T here, and that satisfies some axioms. And this we call a pre-Cartier category with an infinitesimal braiding T, which on the algebra side will correspond to a pre-Cartier bi-algebra with an infinitesimal R matrix chi. So that's the chi that we've seen that comes from the Casimir. So the point of this slide is kind of, we can ask these questions about finding Casimirs on the level of algebra or on the level of category, and I'm going to switch a bit back and forth because both sides are basically the same. And here it's just written how you should think about these new structures. So think of an infinitesimal braiding as a first order deformation of a braiding. So you start with a braiding sigma, you get something deformed in the first order, and in the same way, an infinitesimal R matrix should be understood as a first order deformation of an R matrix. One quick slide about braided monoidal categories. So I think most people didn't want to know this, but just very briefly, take a category with a monoidal structure that you think of as a tensor product, like with all the properties of the tensor product vector spaces that we don't like. And let's say we have a natural isomorphism sigma that tells you how to flip objects. And this can be written in a graphical way. If you look at these diagrams here, where the braiding is like the overcrossing, and you read this from up to down. And then the rules that this braiding has to satisfy is written here. Like if you braid M with the tensor product of N and O, this should be the same thing of first braiding M and N, and then braiding M and O. Similarly, if the tensor is in the first entry, and if this holds, you can show that the quantum Yang-Baxter, the braid relation holds, which is braiding first two, second two, first two, is the same thing as second two, first two, second two. Okay. So this is the easy graphical slide. There's the technical slide that you're not supposed to read. I'm just saying this is all the information of a braided monoid category, because in principle, if you want to be very rigorous, you also need the associators, the A's that tell you how to rebracket things. You need the unitors, these are L and R, so left and right unitors, how to identify the tensor product with your monoid unit with the objects, and the braiding can be seen as a natural isomorphism of the tensor product with its opposite, satisfying some obvious axioms that we don't really care. Okay, now back to the algebra side. So this was the category side, where we had braided monoid categories, and I claimed on one of the motivating slides that braided monoid categories are the same thing as quasi-triangular bialgebras. In what sense is this true? So if you have a bialgebra, so an algebra where you have also a coproduct delta and a co-unit epsilon, and those are algebra morphisms, then your category of left modules, we write as HM, becomes a monoid category. So we can tensorize left H modules and get a left H module, where the action on the tensor product is simply given by the coproduct on the element. And this is an action precisely because delta is an algebra morphism. So this is why we really need the bialgebra properties to make this into a left module. And in a similar way, you can use the co-unit to get an action on the monoid unit that here is just the ground field. That was shown by Grinfeld and Majid that this category, given a bialgebra, is now braided if and only if H is a quasi-triangular bialgebra. So this means if you can find an invertible element R, this is this universal R matrix that we've also seen, which satisfies some properties. They are written here. So if I apply the coproduct to the first or the second tensor leg of R, I get two copies of R. And then this 1, 3, and 2, 3 is just telling us where the tensor legs are placed in the triple tensor product. So like the R2, 3 means that it's just one tensor R, while R1, 3 means the first tensor leg is on the first, there's a 1 in the second, and there's the second tensor leg on the third tensor. And I also want that this algebra is quasi-co-commutative, so the opposite coproduct is almost like the coproduct, but up to the conjugation with R. That's what we do. Okay, the claim is that so this structure will give us a braiding. And in fact, you can write down this braiding just in terms of the R matrix that acts on your elements. Just as a quick comment, so we call such a braiding a symmetry if it squares to 1. And this happens if and only if R is a triangular R matrix. So if the inverse of R is given by the flipped R, but this is not an assumption that we are using here. We are working with arbitrary braidings and arbitrary triangle structures. Okay, some quick examples so we can think of something here. So what would we have in mind? So if we have co-commutativity, so if delta opposite equals delta, then you can take as an R matrix simply R equals 1 tensor 1. And you can see that all of the axioms are satisfied. So this you can do, for example, if you take a group algebra for any group, or the universal enveloping algebra for any Lie algebra. So this fits very well the motivating example we have seen on the first slide. It's a bit boring, 1 tensor 1, come on, we can do better. So we can do slightly better for the group algebra of the cyclic group. And here we can find the following quasi-triangular structure that is written here in terms of the generating element G. of this group algebra. So here simply g to the power n would be 1. And this is interesting because this is the braiding that actually governs graded geometry. Something we have here. Or maybe not. So for n equal 2, this will give you, for example, the super geometry gradings. This tells you if you flip the two graded objects, you get the Kosul sign that you know from graded geometry. And this is the R matrix structure that's in the background.
So it does remarkably looks like discrete Fourier transform, like that exponential factor.
Yeah, but I'm not sure if that's a coincidence or you know.
Sorry, the JJ and JK, those are
So you sum over j and k from 0 to n minus 1. And so the g, this is the generator of the group algebra. So you simply have that g to the power n would be 1.
okay. So it's power. It's not okay. It's really like a, so
It's not coordinates or something. It's power. As a last quick example, I want to mention the Grunfeld double. It's worked for any finite dimensional algebra. You can take this dual combination, so the linear dual tensor Hopf algebra, and this is a quasi triangular Hopf algebra where you take as an R matrix to be this guy, where you sum over the dual basis. Yeah. See. So now coming to our definition, because we said so we want to look at first order deformations of these guys. So the way of thinking is like this: we start with a bi-algebra H. We take Common power series of this bi-algebra, where we extend all of the algebraic structure in H bar linear way. So the product, co-product, everything is just the H bar linear extension. And then this is what some people call a topological bi-algebra. You have to be a bit careful with the tensor product, but we don't care at the moment. So let's say on this topological bi-algebra, you have a quasi-triangle structure that we call R tilde. So this actually gives us a lot of information because we have a series, like a formal power series, and like in each order, some things have to be satisfied. So let's read this in low orders. In 0 order of H bar, so I can write R tilde just as R plus higher orders. And this R will give us a quasi-triangular bi-algebra structure on H, on the bi-algebra you start with. In particular, R is an invertible element, so you can factor this out, and you can write your R tilde in this way here, which then gives you something in first order, whatever this is, and you call it chi. And so what we did, we were kind of interested in what is this chi, what kind of axioms does it satisfy. So what are the properties of this chi? And yeah, this governed this definition here that in principle now is independent of any common power series, but is of course motivated from this common power series picture. And so we say that a triple HR chi is called a pre-Cartesian bi-algebra with an infinitesimal R matrix chi, element of H tends to H, if first of all H and R is a quasi-triangular bi-algebra. And now chi has to satisfy all of these properties. So first of all, it has to commute with the image of the coproduct, just we have seen with the Casimir. And then kind of satisfy these two primitivity properties. I mean, it's almost, we sometimes call it a braided primitivity. Whatever this is, yeah. If furthermore, your R matrix and chi commute in this way here, we call it a Cartier bi-algebra. And I'm also going to motivate the naming in a second. Okay, that's the definition, and the take-home message here would be that we are just reading it from what an R matrix from the power series gives you in first order. That's kind of the take-home. And maybe the rest of the talk will be trying to justify why is this an interesting definition. So first of all, a proposition that goes back to the statement that category theory and algebra are the same stuff. So if you get some definition on the level of algebra, we have a similar definition on the level of modules. And so this proposition tells you if you have such a pre-Cartesian algebra, this you get if and only if your category of X modules is first of all a braided monoid category. This we know because part of the data is an R matrix. But we have this chi, some extra, and so this chi will give rise to a natural transformation T m, that you can see is not flipping stuff, so it keeps the order. It's a morphism in the category of left modules, and it satisfies these two properties that look a lot like the twisted or the braided primitivity axioms. And if, in addition, it's a Cartier bialgebra, so if R chi equals chi of R, then we see that this reflects on the fact that the braiding would commute with the infinitesimal braiding. I didn't say that T is the infinitesimal braiding, but that's not the definition. So we simply make this proposition into a definition, and we say that a braided monoid category with a natural transformation T satisfying all of this is called a pre-Cartier category, called T the infinitesimal braiding. So why this pre-Cartier name? Part of this was known in the literature. So for symmetries, we call that this meant, so if sigma squares to 1, and if also sigma commutes with T, we get back the notion of Cartier category introduced by Cartier in 93. So there's also a nice chapter about this in the book of Kassel, and more recently in the paper of Berger and Rami. And because our definition is more general, we didn't call it Cartier, but pre, because it's that's the motivation. Okay, I'm like halfway. Okay, I have half an hour, but I'm not halfway through the slides, so let's see how much I can do. Yeah, I think it's good to see some examples. The first class of examples is the trivial one, which is a bit boring, but so you see, you can easily see that the space of infinitesimal R matrices is a vector space. So in particular, you can always choose chi equals 0, and it will satisfy everything. But again, it's a bit boring. It's something more interesting. So quasi-triangular Lie algebras fit the definition. So you take a Lie algebra G with Lie bracket, and a little R matrix. This is an element of G tensor G. It has to be at invariant and satisfy classical Yang-Baxter. That's written here. If you have such a guy, then you simply symmetrize your little R matrix, and you get a chi that then satisfies all of the axioms for the Hopf algebra, universal enveloping algebra with capital R matrix 1 tensor 1.
Because then you control it to 0. So it's a symmetrical part to the
Maybe, yeah. Maybe you're right. Okay, to be checked. Yeah.
Sorry, I haven't heard the question, so maybe I'll ask the same question. In the second example, would it be enough for only the symmetric part of R to be at invariant?
It was exactly this question, and I think you guys are right to observe that. So,
Okay, thanks.
very good observation. Yeah. You pay attention, this is great. And okay, maybe I skip this one. This is like the commutative case, maybe not so interesting. Okay, let's look at something more interesting that is like a mixture of a universal enveloping algebra and a group algebra. Those are the so-called EN of algebras introduced by Redford and others. So as an algebra, this is generated by G x1 until xn with the rules that G squares to 1 and the xi and xj's anti-commute, also with the x and the g's, which then tells you get a vector space of dimension 2n plus 1. And this becomes a Hopf algebra, bialgebra with the following rules that G is a group-like element, while the x's are kind of primitive, but not really. They are twisted primitive, where you see you don't have x tensor 1 plus 1 tensor x, but in the second term, there's a G smuggled in. and this is done in a way that is still a Hopf algebra. What is nice is that for this class of bialgebras, Hopf algebras, people classified all possible R matrices, and they look like this here. And so the input here is an n by n matrix with values in complex numbers, and you simply sum over them here. You look at this terms, and this gives you an R matrix for the En. So what is nice is that you can show that this R is a triangular R matrix corresponding to a symmetry, if and only if your input is a symmetric matrix. So what we did is we also classified all infinitesimal R matrices, and they are of this form here, shorter. And you can show that they are Cartier if and only if the input is a skew symmetric matrix. So what is nice here, you see kind of what we tried in the beginning. So you have some chi, you x potentiated, this is the thing here, you multiply with some R matrix that you have there, and you get an R matrix. So this is kind of built in a way that you already see that this quantization works and gives you some R matrix. But okay, it's just a foreshadowing of what we are going to see later. Just pointing out that this term here appears also here. And some comments on the E1 that maybe I skip. Okay, some properties of the chi are here. So if you are given any pre-Cartier quasi-triangular bialgebra, you notice that the chi is a Hochschild to cocycle, which means that the following formula holds. And it's also fun to show that the infinitesimal quantum vector equation holds. It's a fun exercise. Yeah, you simply write it down. You see it's correct. It's not as horrible as Fritzo's term that we saw last seminar, but it's, I would say, also a scary formula.
Braidings for its intentionalizer.
So this is there were some partial results about this written by Shan or a special class of examples, but I think this is more general. And okay, maybe now we can go back to some kind of Casimir. So let's say if you have even a pre-Cartier quasi-triangular Hopf algebra. So if you also have an antipode, then you can take the chi here, the two tensor legs, you apply the antipodes to the first one, and you multiply them so that you get an element of 8. And for some reason here we call it gamma. Maybe C for Casimir would have made more sense. But, okay. Anyway, so that is what we call the Casimir in this setup. And first of all, you can see that this is a central element, automatically central. Furthermore, you see that so if you're not in the pre-Cartier case, but in the Cartier case, and you have a triangular algebra, so special, then your chi will actually not be a cocycle, but a coboundary. So you can show that chi is a Hochschild to coboundary, and it's in the image of the Hochschild differential, where you're plugging half of the Casimir. So yeah, kind of interesting that the pre corresponds to cocycles, while Cartier corresponds to coboundaries. Good. So what is next? So this is now building up for the second part. We have seen that if we have a formal power series and we ask for an R matrix, we can factor out the lowest order, we get some chi, and then this gives us the datum of pre-Cartier quasi-triangular Hopf algebra. So the question is, can we do other way around? So let's say we are given the datum of H, R, and chi, can we find the R tilde such that one holds? So can we quantize chi? That's kind of one of the motivating questions. And so we can play a little bit with examples. So for Sweetler's Hopf algebra, it's the En algebra for n equal 1, the smallest one. This works easily. So you simply take R times x of chi. In this case, it's not really an exponential function because it terminates in the linear term. So all higher terms vanish because you know that x squared equals 0. So you really just get this here, and you can verify by hand that R tilde is an R matrix. So this works well. In more general, if you go for any EN algebra, you plug in a chi that we found. This will give you like n terms, and you can also verify by hand that this is an R matrix. So this works well, and it's kind of naive formula that we found works, and we don't need any fancy stuff here. This on the nose gives us quantization of chi. But okay, these are just examples. Can we say something in general? And yes, we can. This is now part of this second paper that I'm going to talk about. But yeah, for this, the price we have to pay is we have to understand something about quasi-bialgebras. So this means these re-associators will enter, and formulas that you've seen that were already kind of ugly are becoming even more ugly. So that's the price we have to pay. So bear with me, we can get through this. So here a slide to explain what is a quasi-bialgebra. So you start with an associative algebra H, and you have two algebra morphisms, delta and epsilon, that are of course your coproduct and your co-unit. But now you are only asking for like a quasi co-associativity. So you say, you call this a quasi-bialgebra if you find an invertible element phi, this re-associator, and invertible elements L and R in H, such that these formulas hold. And here, like on this slide, and also on the following, if you kind of blend out the blue part, you will get the usual definitions that you're used to. So what usually just a bi-algebra is, and the blue part is the new part, the quasi part makes things more complicated. So here you really think if you set phi and L and R equals to 1, then you get that well-known definitions. There are some extra properties that have to be satisfied, but it's not too crucial. Maybe more interesting is we call a quasi-bialgebra quasi-triangular if we find an invertible element R. So here we think of the R matrix. But now you can see that it's not exactly the hexagons we have seen on the previous slides, but they are twisted a bit using this phi. So just mixing up stuff, and that's the definition of a quasi-triangular quasi-bialgebra. Okay, of course you memorized all of this with all the correct indices. Perfect. So let's continue. And then, yeah, using the same approach, we can cook up a definition of what is an infinitesimal R matrix in this setup. So if you are starting a quasi-bialgebra rather than a bialgebra, then you can simply make this definition that you want some chi satisfying these equations here. And again, just don't really look at the blue part, only look at the black part. And this is what we had in the previous slides. We're just mixing it up using this. And okay, this is the Cartier condition, a small theorem that you can prove. Part of this is very well known. And here I should say that I was lying a little bit on the first slide when I said that bialgebra is the same thing as a monoid category. This is only true if your associativity constraints are the ones of vector spaces. If they are more complicated, you will get a non-trivial phi. So the actual true theorem says if you start with an associative unitary algebra, then the representation category, so the left-edge modules, they form a monoidal category with some functor, blah, 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 if and only if you get a quasi-bialgebra. And then you see that your associators of your category are governed by this re-associator, while the left and right unitors are governed by N and R. But yeah, this is again just confirming this statement that algebra and category are the same thing. Great. Yeah.
Is there a way to hide all blue stuff by saying that you're working in some deformed category or something? Or not really?
we need trees, and then we do those strict manual. Then it's trees managed.
Yeah, I mean,
What's the category? It's like the category of what?
You have a manual category, go to a strict one. This is fighting you with the constraint, right? So you can use the tweets for these guys that's you look for it by 100%.
Okay.
And so these tweets bring you, there is a tweets that bring you to strict manual. And if I disappears, then it's just a button.
because I think you can always strictify in that sense, but then this will mix up your category in a non-trivial way, so you don't have much control. Equivalent to it, you don't know exactly how it looks like this. You don't have control over this switch.
Well, as much as you can have control of the strict manual, you can manually every method is put into strict one.
Sure.
So
In that sense, yeah. No, it's true that in like most papers, people don't really care about this because it's very painful to work in this setup. Just we kind of need it here because we really want to, we had to understand what is going on in this non-strict setup, and just in the end, conversation will end up there. And so, okay, this was the price we pay is like worrying about fines, and yeah. It's not complicated, it's just cumbersome. Okay. And okay, here, these parts we have seen before. So this category is graded if and only if we have an R matrix, and your grading corresponds to the R in this way here. It's a pre-Cartier category if and only if we have a pre-Cartier quasi bialgebra, and the infinitesimal grading and R matrix correspond to each other in this way. And Cartier if and only if the grading and infinitesimal grading commute, which then is reflected on the algebra side by R pi equals chi over R. So some proposition, how can we build more of this quasi-triangular pre-Cartier quasi-bialgebras? You take one of them and you take what Castle and other people call a gauge transformation, so an FM phi. That is just an invertible element of H tensor H. So usually you might think of a Dirichlet twist, which would be an invertible element that is also normalized and also a two co-cycle, but here you really just want an invertible element. And given this, you can twist all of its structures. For example, your co-product is like you have F minus one, we're mixing this up. You are twisting the associator using the failure of the two co-cycle property. You are twisting up the unitors using the failure of F being normalized, twisting R and F, and you get another pre-Cartier quasi-bialgebra. This is just a way to create more examples. So could there be a typo on the probably R? Sorry, which one? Zero, right? Ah, yeah. This is of course F of R F. Yeah. Yeah. So there should be an R in the middle. Huh? Very good. Because otherwise it would be F of. It's not a number. Okay. Of course, the boring example. So we get a pre-Cartier quasi-bialgebra by just looking at bialgebras. So we just take phi and R equals to 1, but that's not really what we want, right? So let's take the EN algebras and let's gauge twist them with a non-trivial twist. And there's a particular one that we can take, and we can reveal it right away. So if we take as a twist 1 tensor G, and you see that, so you start with an honest bialgebra, but using this twisting method here, you get an honest quasi-bialgebra in the sense that here you have a non-trivial associator and the left unitor is non-trivial, while the right unitor is trivial. Your R matrices and chi's are mixed up a little bit. This is like one of examples you can look at. And to be fair, it's not easy to find examples because you really have to take care of a lot of structure, and yeah, it's a mess. Yeah, we have some of them. Very good. So now I have like 10 minutes, maybe, or something.
Oh, I'm not sure. I mean, we started a bit later, right?
Yeah, okay.
Was it at 10 or 15 when we started?
Let's, yeah, maybe 5 minutes later or something.
Okay,
Okay, so there's a last technical thing that I have to talk about, and then it will only be theorems, and then we are done. So the last technical thing, I try to make it easy because it's kind of, it's, I don't know, like it might be a bit difficult to introduce what a Drinfeld associator is in a seminar talk. People have never heard about this, but I try to make it understandable. So first, we should understand what the infinitesimal braid relations are. They are written here. So you just take a family of elements that you call A, I, J, upper indices that run from 1 to 4. And you want certain commutators to vanish. And like the first, sorry, maybe first look at the second commutator, very good choice. Huh? So the second commutator tells us that if the indices of A are different, so the left ones and right ones are different, the commutator should vanish. While the first one tells us if the two indices of the first entry match the first the index of the second ones, then the commutator should also vanish. Okay, and this is what Kono and other people call the infinitesimal braid relations, and they will become important in a second.
Do you really want this to be up to 4 only? I mean,
Yes.
I mean, no, I mean, the you only have 4.
Yes.
Okay.
It will be clear
Okay.
later on, but that's what it is. Yeah, and I don't want to comment further on this now, but it's
Okay.
It's 4. Yeah? It's not 4. Okay, like in a nutshell, a Drinfeld associator is a Hubble power series where you plug in, so you can plug in two things, A and B. Just think of some symbols, whatever, and you get some formal series in A and B. So it has more properties, namely it is nice to solutions of the infinitesimal braid relations. You plug in those guys, the Drinfeld associator is very happy, and it gives you something meaningful. Yeah. So meaning you take some Aij satisfying the upper guys, you plug them in this strange way, you multiply them, you get like this holds. Yeah. And we have many more nice technical properties, but in a nutshell, this is what a Drinfeld associator does. Yeah? And we only have to know that these guys exist. Think of the KZ one that I mentioned in the introduction. And give you the full definition, that's this one, but it's impossible to understand this in a seminar talk. So it's a series that satisfies a lot of complicated properties, but I think the take-home message is really you have to find solutions of the infinitesimal braid relations. You plug them into the associator in some interesting way, and you get a relation like this here. That's kind of the very rough thing what a Drinfeld associator does. Okay, you've seen the full definition, you understood and read everything, very good. So now the task, maybe I'll go back just a second. The task now for us was we want to find the capital A's. We want to find elements that satisfy these infinitesimal braid relations, starting from our setup. Yeah. So let's take a pre-Cartesian category. Recall this: we have a braiding. We have the braiding sigma. We have an infinitesimal braiding T, and now we want to find this capital A's. And so the candidates are written here. So we want to take the T and build the A's out of T. So there are some easy cases, like for example, T12. T12 is very easy because it's just I apply T to the first guys and I do nothing on the third guy. But now T13 is complicated because I want to apply T to the first and the third guy. But this I can do in several ways. Like I can have T on the left side, use the braiding to move Z to the middle, apply T and then braid back. Or I can have t on the right. I apply the braiding to the first two x to the middle slot, apply t and braid back. And it's not clear what my t13 should be. Yeah, is it the first one, the second one? Yeah. The good thing is, what we realized is it doesn't matter because all of these possible combinations that you can think of to build t13 gives you the same thing. Like it's non-trivial to prove, but the two diagrams here coincide. You can kind of transform into each other. And now there's the fourth thing. So similarly, you can think of you want to apply a t in a 4 tensor product to the first and the last one. So you can either rate the like this, then apply t or break back, or do all kinds of strange combinations here. All of these are the same. So all of what's written here is just to say all combinations here give the same outcome. This is great because now we can simply take any of these and call this the Aij. Here it's t because it comes from the infinitesimal braiding, but this is what our Aij's will look like. And this is also why it's 4, because we are living the fourth tensor power. So it's something that happens on the fourth tensor power. And okay, so also this slide is a bit unreadable. The only thing you should read is the last sentence. So this is just to tell you, okay, we have all of these t's. Maybe we should have called them A. The thing is that they isomorphisms in our category, and they satisfy infinitesimal braid relations. So braid, we have found them as an input. Take any pre-Cartesian category. We solve the infinitesimal braid relations using these guys here. Wonderful. So what we will now try is use the Drinfeld associator to create something out of these guys. And that's in fact what's happening here. That's the first main theorem that first tells us, okay, so in the Cartesian case, so when we have also commutativity of braiding and the infinitesimal braiding, you take any Drinfeld associator, psi, then you get a braided monoid category that quantizes your input category. So what you're doing is you simply take the same objects, but you deform the associativity constraints in this way here. So the new A is built out of the old A's, but you also mess them up with capital psi, so the Drinfeld associator, and you see that the infinitesimal braiding enters here in both slots. So this is complicated. But what's very easy is you can quantize your braiding by simply taking the old braiding and composing the exponential of the infinitesimal braiding. So this kind of naive formula that we started with really gives you a braiding in this category if you just use your Drinfeld associator to scramble a little bit associativity constraints. And yes, that's the first theorem. So we can really quantize these braidings. If you want to do the pre-Cartesian case, so if you do not want to worry about the braiding commuting with the infinitesimal braiding, you have to ask something extra. You have to ask commutativity of the t's in this way. And then you can use the same formulas to get braiding even with the same associativity constraints. So here the formulas simplify basically because we are asking the associator to terminate in low orders. Okay, so I'm almost done. So this is everything on the algebra level. So we had the statements on the category level. We can redo everything on the algebra level. I'm not going to torture you of going through all of this, just saying you can find solutions of the infinitesimal braid relations also on the algebraic level. Actually, here you get two nice families. If you have a non-trivial associator built out of the infinitesimal R matrix, you show that you get a nice, quotation marks, quantum Baxter equation here an infinitesimal version that barely fits the screen, but yeah, it holds. And yeah, the same theorems that we had on the 2 slides before that also hold on the algebra level. And there they reach if you start with a Cartier quasi-bialgebra and you take any Drinfeld associator, you get a topological quasi-triangular quasi-bialgebra on from a power series, where you really have now, you can get your R tilde that you see in 0 order is R, if first order is R times chi, then it has higher orders. And the new re-associator that you have to use is built out of the Drinfeld associator. So yeah, this is solving the initial question. So if you are given R and chi, can I get the R tilde? The answer is yes in this case, and this is how to build the structure. If you ask more, so if you ask one of these 3 conditions here, you can even do the pre-Cartier case, and basically you get an R matrix on those. You do not even have to change the associator. And I think now, since I'm basically out of time, this is an example that we spelled out explicitly. So we start with the En of algebras, and then you can do 2 things. You can either first gauge, twist them in the way we have seen, or you can deform them to get some R tilde or R and chi, and then gauge, twist, and both give you the same outcome. We just spelled out how the deformations look. It's of course not super interesting, but here are the formulas. And this is the gauge twist. And I think with this, I thank you for your attention.
Thank you very much. Also, thank you for keeping in time, even though we started later. But it's very good. So, any questions?
Observation of Drinfeld associator consider not for elements.
Not for elements, but
So there you consider 4 elements specific, but it uses infinitesimal gradient. So a priori you consider 4.
Repeat the question.
The question is, I understood is that so for me the Drinfeld associator was defined with properties on a family that satisfied the infinitesimal rate relations, and this family was indexed by the indices of 1 to 4. And your question is if I can do something with more indices. I think in principle.
Okay, so here we have a more special situation of the problem, but this relations that are with the great relations with the level of indices.
Yes, so I'm not sure. I'm not an expert on the Drinfeld associator side, but I expect that this is like the crucial part is you have to understand this for the 4 indices, and then you can extend it to higher ones.
Yes, but
down, please.
oh, sorry.
Yeah, please.
It is true that you can consider any n for the definition of the infinitesimal braid relations. I mean, the Drinfeld associator takes in account just 4 indices, but you can have any n for the relations. If I got the question.
Yeah, excellent. Yeah, that was the question.
Yeah.
Thank you.
I guess one can say the name is Drinfeld-Kono algebra. If you want to.
Exactly. Yeah.
Any further questions?
Can I ask? I think in the previous slide you had this Cartier and pre-Cartier cases with theorems.
Yes.
And in the pre-Cartier case, there was basically the infinitesimal braidings had to commute. I forgot, what is the pre-Cartier case?
So this is where we do not ask the R matrix and the chi to commute, which would translate into the braiding and infinitesimal braiding to commute. So we're we're not asking this. This is just asking the. I could go back to the very different definition, but we're not asking this.
No, it's fine. You are saying that the infinitesimal braiding is not symmetric anymore. I see. And okay.
We are not asking this last line here. Yeah?
Oh, I understand. Thank you. Do you agree that the condition is very strong? You have to have in the pre-calc here. Okay.
You mean in the
Andrea
theorem or
is saying yes.
definition?
In the theorem.
In the theorem. Yes, it is
Do you
very
have
strong.
do you have some examples where?
Yes. So this condition here, for example, so you can choose one of them and then you will get the others for free. So this is very strong. And in fact, it leads to the principal associator
Being zero, right? Because
in first order. So it's
because
really
like this is
basically saying that you can keep the associators and you don't have to change this. Huh? And for example, you can take any.
Is there? Sorry. You can okay, sorry, you can finish.
Yeah, but I wanted to say if you are asking for examples where this is satisfied, you can take any of the Pn algebras with any R and any chi, and all of them will satisfy this.
Oh, also so they're the coarse commute.
Yeah.
The infinite. Okay, I see. Okay, that's interesting. Thank you. Is there hope to have a non-trivial, like let's say less restrictive condition in this theorem?
I mean,
because as you say, it kills the whole associator.
Yeah, we were trying to find an example, but we could not. So that was really the best thing that we could do. We actually think that maybe you have to choose a different R in the setup. Maybe the exponential is not working, but you have to look at something more complicated. But we don't know what to take here. It's I don't know.
Okay, and so can I ask one more question?
Sure.
When you define these infinitesimal braidings with multiple indices like chi1, 3 or so,
yeah.
you have to because you are now in a braided setting, you have to choose how to braid those strands together, and then you show that some of them are equal. But is there like a principle one should have in mind that as you go all the ways over from the left and here I was not able to parse it.
Here you see the four possibilities, and the rule should be that you should have the same amount of sigmas and sigma minus ones. Yeah. And
on each couple of strands or something like that.
Yes, on each couple of strains. Yeah. But apart from that, like any combination you can think of gives the same outcome.
Okay. Thank you. Thank you. That's Thanks.
And that's something we did not think that would actually work. We were kind of puzzled why this works. It's a bit too good to be true, but you can show that.
Yeah, this is clear if the braiding is symmetric, but if it's not, it's a bit less clear.
Why do you have an intuition why it works? Like, because you did the computation.
Yeah.
I don't know the bigger reason why this works. I mean, of course, it follows from the definition, from the axioms, but I don't know.
The intuition was actually in the first paper of Thomas. So if you go back some slides, when you talked about the properties of chi, so being before the quasi case. So yeah, here, this theorem, if you look at this theorem in the non-symmetric setting and in the categorical setting, gives you that property, more or less.
Yeah, so it's maybe related to the fact that you have a whole co-cycle. This is what you're saying.
Yeah.
Okay, thank you.
Okay, if there is no further questions, then let's thank Tomasz again for the report.